Hi everyone, this is Xinle Cao, a third-year PhD candidate at Zhejiang University. Today I'm going to present our paper named Frequency Revealing Attacks Against Frequency Hiding or Preserving Encryption. Firstly, let me introduce the background. With the popularity of cloud computing, data owners would like to store their databases in the cloud to save the costs. In the simplest scenario, there is only one client and one server. The client uploads the database to a server, and in the future, it issues queries to the server to access the database. The server will process queries and finally return query results. To protect the security and privacy, the client requires everything observed by the server to be encrypted, including the database, the query, and the query results. But preserving encryption is a technique presented for this scenario. We give a simple example here. Roughly speaking, this encryption preserves plaintext order in ciphertext to allow direct comparison operations over ciphertext. This encryption enables efficient range queries because the server can make use of some optimizations to process range queries. For example, the server can organize ciphertext as a search tree, like a B tree and a B plus tree. Please note range queries are important and common in database queries, which makes OP valuable in encrypted databases. However, the security of OP has been debated for a long time. Initial OP works leak both plaintext order and plaintext frequency to the server, and possibly an attacker who can access the server. A line of works have shown that the attacker can successfully recover most plaintext with frequency leakage. To this end, recent works focus on protecting the plaintext frequency. Some OP schemes named frequency hiding or preserving encryption are presented. These schemes randomize ciphertext of repeated plaintext to hide frequency. We also give a simple example here. There are two repeated plaintext array in this example, and they are encrypted to different ciphertexts 1 and 2. These schemes are regarded as an important step towards enhancing the security of OP. Up to now, there have been 3 FHTOP schemes proposed in both security and database communities. They claim they can avoid the leakage of frequency. Unfortunately, all of them are broken now by our new concrete attacks named frequency revealing attacks. Here we give a brief look at the attack results. We note our attacks, frequency revealing attacks, are designed to recover frequency. So in this figure, we saw the recovered frequency. The black curve represents the real plaintext frequency distribution, and the other 3 curves represent the frequency distributions recovered by our attacks from the 3 FHTOP schemes. The vertical shifts between these curves are just used to show the curves separately. They do not mean there are some gaps between these curves. So removing the vertical shifts, we can see the 4 curves are nearly identical, which shows our attacks effectively recover plaintext frequency in these schemes. Now let's see some details about how our attacks recover frequency. We note there are some theoretical results and formal proofs in our paper. Here we just introduce some intuitions. If you are interested proofs and theoretical results, we refer to our paper. So the first FHOP scheme is Kurzbaum's FHOP. It indeed guarantees that each plaintext is encrypted to a unique ciphertext. However, the ciphertext distribution in this scheme is non-uniform and thus leaks the frequency. In the first figure, we saw the ciphertext distribution of an example. The horizontal and vertical axes represent the ciphertext order and the ciphertext value, respectively. If the ciphertext distribution is uniform, then the value should increase uniformly with the order increasing. But we can see the value actually increases non-uniformly. Besides, we mark ciphertext having distinct underlying plaintext with different colors and use blue points to show the bonds between them. Then we can see there is an important and unnatural phenomenon. It seems its blue point is located near a twinning point. Look at the first blue point. The value increases faster on both its left and right. To show it more clearly, we also give the ciphertext distance distribution in the second figure. Now the vertical axis represents the distance between neighboring ciphertexts, which can be regarded as the increased rate of ciphertext value. Then we can say it's true that on the left and right of each blue point, the distance is larger, which implies the value increases faster. For the other two FHOP schemes, attacks are more general because the two schemes can guarantee uniform distribution. Suppose there are some ciphertexts stored in the server and some new ciphertexts are going to be inserted between the older ciphertexts. Then if all the ciphertexts have the same underlying plaintext, then the two schemes will guarantee that the insertion happens uniformly. That means new ciphertexts are inserted uniformly between the older ciphertexts. But however, when ciphertexts have distinct underlying plaintext, the insertion can be non-uniform. For example, we use red and purple balls to represent ciphertexts having distinct underlying plaintext. Then in reality, there are possibly too many red balls and a few purple balls inserted, making the insertion happen non-uniformly. Our text apply this observation to distinguish ciphertexts having distinct underlying plaintext and those having the same underlying plaintext. Besides, we want to note a worse but common case in reality. Suppose there are some new distinct plaintexts to be encrypted and inserted. Then we use the green balls to represent this ciphertext. Then this ciphertext, all the green balls are inserted exactly the same one position between all the ciphertexts, which indicates the insertion is very, very non-uniform. Then we can infer the insertion belongs to some new distinct plaintexts with high probability. Now let's see some experimental results. Actually, it is very challenging to exactly recover frequency because there are some randomness in all the three FHOP schemes. But on the small estimation error, the accuracy of our text is more than 90%. Moreover, the false positive rate is no more than 10%. We note the false positive rate means our text output some ciphertext having the same underlying plain text, but our texts incorrectly think they have distinct underlying plain texts. We also validate our text by combining them with prior attacks to recover plain text protected by these FITLB schemes. The recovery rate is nearly 100%. In this experiment, the datasets are somehow special as the plaintext spaces in them are relatively small. They are no more than 31. But still, the recovery rate on these datasets is unacceptable, since these datasets are still common and important in reality. Finally, in the future, we will continuously study two questions. Firstly, we want to combine our text and prior text to attack more datasets in reality where the plaintext space is larger. Secondly, we will try our best to enhance the security of OPE, as OPE is so suitable for encrypted databases. That's all. Thank you.